A confirmation about the audio, please, guys. If you're able to hear me out perfectly well, kindly confirm the same. Thank you. We shall be starting in a couple of moments. Yes, Pranay, a new cyclonic circulation is developing. And I think you have attended the portion about naming. Today, we will cover the portion of naming of cyclones as well. So, and the formation of tropical cyclones as well. So, you'll get a better idea. By the way, any issues that you guys are facing in the portion that we have covered till now, kindly let me know. Okay. So, hello, a very warm good morning to all of you, and welcome to Byju's Exam Prep IAS. Welcome to another session of geography. Now, today's session is going to be from 10 to 8. We are going to have a lunch break at 1, and 1 to 2 is going to be lunch break, and again, snacks break is going to be from 5 to 5:30. So that is going to be the schedule. In the meanwhile, we will be taking breaks in between as well to make it more tolerable for you guys as well, so that it doesn't become oppressive as a particular lesson or a chapter. So here we start with the portion of atmospheric circulations. Where we left off yesterday was the discussion about the basics of atmosphere, the basic concepts about heating, distribution of heat, advection, convection, conduction, all those basics we have covered yesterday. Now, today, all the various different topics and chapters that we are going to cover, that is going to be a mere implementation of what we have studied yesterday. We are going to take a look into the practical application of it. Now we start with the portion of atmospheric circulation. And let me be very clear, this particular portion of atmospheric circulation, if you get to know this, if you understand this, then understanding and deciphering the global climate, global climatic distribution, the various different rainfall patterns which occur across the globe, Indian monsoon season, also cyclonic circulation, everything will be very easy to understand if we get a clear concept of the wind systems which move across the planet. So in this portion of atmospheric circulation, this is relevant for your prelims and the mains examination as well. In the prelims, you get questions from the area of local winds. Permanent winds is also something that you get questions about. Permanent winds, regions, and properties. Okay. In the mains exam, other than that, local winds, types, only the major ones. In the mains exam, again, you can get a derived question, not a direct question, a derived question from the aspect of pressure belts. Pressure belts. Okay? Derived questions. We'll take a look at the type of questions which can be framed from here, and we shall have a better understanding of this. Namita, Milankovitch cycle basically is what was, first of all, understand why Milutin Milankovitch came upon with this idea of Milankovitch cycle. He wanted to explain why is it that on the planet every few thousand years we experience extreme cold conditions, whereby the polar areas, the subpolar and the temperate regions, they get frozen, what we refer to as an ice age. And again, they melt, as is the situation now. So that is what he was trying to explain, the ice age. And he could explain that with the aspect of the movement of Earth around the sun, whereby he postulated that, look, Earth is not always going to rotate on a elliptical orbit. Sometimes it is going to take a spherical orbit or a circular orbit as well, influenced by the gravitational pull of attraction exerted by Jupiter and Saturn as well. So as a result of that, the Earth's orbital movement undergoes a change. As of now, the present scenario is Earth is closest to attaining a circular orbit. But every 1 lakh years, it changes from a circular to a highly elliptical orbit where the distance of aphelion and perihelion, they are very, very large, which can bring about very significant rate of cooling. And he also talked about the fact that the axial tilt that we talk about, that also ends up changing every 14,000 to 15,000 years, in between 24.5 to around 21.5. That is the variation in axial tilt. Along with that, he also talked about the wobbling of the planet. That planet is not always fixated like this. It is just like any sphere that you rotate. That sphere also wobbles at the end of it, changing the amount of solar insolation received. So with the help of these three movements, he could explain that why some areas for a prolonged duration of few thousand years will experience very little solar insolation, why it will lead to significant amount of cooling, and then again a subsequent heating. That is the Milankovitch cycle. And Ajit, there will be no snowfall in coastal regions due to lack of extreme weather conditions. In majority of the coastal areas, you won't experience snowfall unless and until it is in extremity of latitude. That is very high latitude. If it is there, only then snowfall will be observed in the coastal regions. Otherwise, even if you take the case of, let's say, United Kingdom or Britain, now across the similar latitudes, if you go into Russia, if you go into Poland, across the similar latitude, you will experience snowfall. But because Britain is impacted by oceanic winds and the sea winds coming frequently and the presence of water vapor, they experience a moderate climate and devoid of snowfall. Okay. Utkarsh, westerlies, what westerlies are, what Lu is, we'll talk about that. Okay. And Pranay, after revising classes, it is better to take classes or not. I really see you should attend it as long as your concepts, they keep on getting polished, right? So it might be possible that in the first session you have few of the loopholes in the entirety of the syllabus. So in that case, it is justified for you to have another go at it, unless and until all the various different loopholes are patched up. And once that is done, it is very important for you that even if you are attending the sessions, it is very important for you to be studying on your own as well, and making your own notes, topic based notes, writing it on the piece of paper that what do you understand, let's suppose, what do you understand by temperature inversion, what is it that you understand by the layers of atmosphere, what are the properties of troposphere. So there you should be able to create and carve out your own notes along with the rough sketch and the diagram. Now that is going to give you a lot of understanding in terms of what are the areas that you have not understood, what are the areas that you are finding it difficult in. Because trust me, it happens when you study the book, when you are reading the book, always the perception is that I know this also, I know that also, I know that also. But when you start writing it on your own, there you realize that there are a lot of different concepts that you have simply overlooked or looked at it from a shallow level. So that kind of introspection is very important. And Abhijit, Northern Plain currently is experiencing cooler weather in May, which is usually unlikely. Is there any reason or local disturbance? So, Abhijit, understand that till last month, there was a significant amount of western disturbance which created thunderstorm and colder conditions. Even this time, in a significant portion of northern India, you have the impact of western disturbance. What western disturbances? We will come to it when we study about Indian climate and Indian monsoon. But then there is a significant low pressure which has developed right now over the Vidarbha region of Maharashtra. That is, the eastern part of Maharashtra has observed a development of a very significant low pressure. Simultaneously, there is a low pressure developing in the region of Bay of Bengal as well. So both of these systems, they are acting simultaneously, creating a bout of rainfall in these areas. And as we move another week, many areas, especially across the eastern part of the country and the southern part of the country, they shall start experiencing pre-monsoon showers. So whenever there is a subsequent occurrence of rainfall, automatically the weather conditions, they will cool down. Okay. And last question I'll take is of Roshan. How to make notes? Roshan, when you understand first of all that when you are making notes, what is the purpose of it? The purpose is not to be circulated in the market. The purpose is not to have a beautified copy which is rewarded in your school days, that look how beautiful this copy is, look how beautiful this notebook is. That is not the purpose of note making. Purpose of note making is to enable you to revise. So when you are creating or crafting a note, understand it should be very brief and it should contain all the concise points that you would want to recall. And the purpose is that, let's say, the entire portion of climatology that you will study, if you have concised them in 4 to 5 pages, then before the examination, rather than reading through the book, just those 4 to 5 pages, a quick glance of it will do. So bullet points, and also only the main points. So in the first reading, when you are trying to create notes, only after reading it one time, each and every topic will seem important. And that goes true for all the subjects. If you are studying history, polity, geography, any subject, if immediately after reading it for the first time, you have not read that particular topic ever, and you're reading it for the first time, each and every sentence will seem important. So the notes that you will make will be very redundant. So always I would advise that while carrying out your revision, after revising a particular chapter, not reading it, revising the particular chapter, you have to, or you should try to close all the books, and then in a piece of paper, the bullet points about what is it that you recall about that point or that topic. That is something which is going to help you. Okay. And generally, how many days it will take to make notes? It depends on individual as well. It depends on your personal capacity to revise as well. Ambika, understand that. But ideally, I would say that for any module that you are revising, so shorter time period it will take for you to revise, shorter it will take for you to create notes as well. And how do we understand how long a time period will it take for me to revise? How sooner are you carrying out the revision? For example, today the topics that we are going to study, let's suppose few of us, we have a kind of an inkling in the mind that, okay, anyways the recordings are going to be available, I will revise it at the end of May. That end of May will never come. So if you revise it within 7 days of what you have studied, it will take very short period of time to be able to revise. And then if you create notes, it will be a faster process. If you create notes after, let's say, 1 month or 2 months, it will be a very long-term exercise. Okay. And is it okay to make notes only for mains exam? For every concept, any concept that you come across, because you don't know what questions will be asked for mains and what questions will be asked for prelims. And this is the biggest fallacy in terms of preparation, when candidates say that I'm preparing for prelims right now, I'm preparing for mains right now. Ideally, all the preparation should be targeted towards mains exam only. And because understand the simple logic, anybody who tells you that they are preparing for prelims, that simply tells them that or tells you that it is the final goal. So you will find many candidates who will come to you and who will tell you that I have appeared in the mains for 6 times, 5 times, 4 times. So that is where the preparation aspect has to change. You have to target the syllabus, mains portion. You have to target how do you achieve a good rank. Prelims will be prepared along the way. So never have a separate preparation for prelims. 2 to 3 months before the prelims examination, then start focusing on the prelims examination by taking a look at the previous year questions, adding to your knowledge arsenal, and appearing for as many test series as possible. Okay. How to prepare geography for prelims. Okay, that is what I was telling Gayu. I hope you got the answer as well. Prelims, first of all, cover all the basics. There should be no loophole that this is for main, so I will not study this. Every portion of the basics should be studied. Once you have done that and you have done the portion of answer writing as well, your understanding will develop much greater to a significant extent. And when the understanding is taken to that level, then after that, a focused approach 2 to 3 months before the prelims would be sufficient. Okay? Right. So now we start with the portion of atmospheric circulation. Here we shall be introduced to certain concepts. For example, what is atmospheric pressure? Why is it that the winds move? What are the factors contributing to the wind movement? We are going to study about Coriolis force. What is Coriolis force? What are permanent winds? What are local wind systems? And what are the various pressure belts across the planet? What is the ideal condition for the movement of the winds, as shown or indicated in all the diagrams or the notes that you will find across the various textbooks, across NCRTs, everywhere, the relevant diagram that you will find, and what actually happens. What is the reality? That is also we will try to indicate and we will try to study. So after that, we shall be moving into the portions of humidity, precipitation, types of rainfall, cyclonic events, and also atmospheric phenomena like jet streams, El Nino, La Nina, etc. Okay. Now, here we start first of all with the aspect of pressure. What do we understand by pressure? So pressure is not a particular term associated only with, let's say, geography. When you hear about pressure, pressure is what? Force per unit area. It is a physics term, right? Term used in physics. But let's suppose we are unable to understand what is force per unit area. Here, think about it that this particular palm of my hand serves as a platform. Now here, if I am exerting a force with the other hand, this palm will experience some pressure. So what is the pressure? Force per unit area. What is the total force I am applying in this small area? That will give me an idea about pressure. Now, when we say atmospheric pressure or air pressure, what do we mean by that? That basically indicates the force or the weight exerted by the air around us. Now, the air around us, we barely are able to feel that air. So how do we understand that whether there is a pressure or not? So air pressure is very simple term. If you understand that, air pressure is basically, if you consider, let's suppose, if you consider the ground surface, now on top of that, let's suppose you consider an entire column of air particles. So the total weight exerted by all the air particles, that is what is referred to as pressure. Okay? Total weight exerted by the air particles on a particular area, that is referred to as atmospheric pressure. This atmospheric pressure can vary. It will never be consistent in the same place, in the same area, between day and night, between, let's say, summer and winter, this pressure tends to vary because the air is never static. Air tends to move from one region to another. Now, the easiest example to understand pressure and the impact of air pressure around us, you would have experienced that presently, wherever you are living, you are very comfortable, you are very good to do, and you don't have any issues with regards to your bodily activities and body functions, because our body is adapted to very high conditions of atmospheric pressure. We are living on the ground surface, obviously, so the body is always adapted to very high pressure. If, let's say, you move in an airplane which has got some amount of pressure discrepancy there, you will observe your ear pop. Or if you are moving high up in the mountains while you are moving through a hill station or going for a trekking activity, or if you happen to go to high altitude regions such as Arunachal or Ladakh, in those areas, suddenly you will start feeling dizzy, you will start feel sometimes your ears will pop, and that is because the outside air pressure is very low and your body's pressure is high. That is why when people go out into the sky, into the space, they have those space suits. Why? In order to adjust to the zero pressure outside. So pressure on the ground surface is going to be maximum because here all the weight is going to be imposed on the ground surface. Now here, let us take a deeper look and a deeper understanding about what do we understand by pressure. So the weight of a column of air contained in a unit area from the mean sea level to the top of the atmosphere, that is what we refer to as atmospheric pressure. Now it is expressed in units of millibar, and the average atmospheric pressure is going to be 1013.2 millibar. That is the average atmospheric pressure in general. So if in any region the pressure comes out to be, let's say, 980 millibar, that is regarded as a condition of low pressure. If the pressure comes out to be, let's say, 1020 millibar, that will always be regarded as high pressure. Now here, let me make myself clear from the get-go that when we talk about atmospheric pressure, regardless of what the common perception is, it is not only driven due to temperature conditions. Pressure is determined by various factors. And the atmospheric pressure that you experience in an area, that in itself is determined by multiple different factors. So here, when we talk about atmospheric pressure, it is dependent on temperature and also movement of air. Sometimes even movement of air can end up creating different types of pressure on the ground, regardless of temperature. Having said that, temperature is one of the leading factors and the leading causes behind creating pressure conditions, high pressure conditions or low pressure conditions. How, why, where, when will come to it. But here I would like to ask you a certain set of questions. Yesterday, most of you, I hope you were active enough and you were awake enough when we were discussing about, when we initiated the discussion about the various different layers of atmosphere, troposphere, stratosphere, weak vertical movement, strong vertical movement of air. I hope that we understood that. So let me ask you, when we talk about a warm air parcel or a warm air column, what will be the tendency of warm air? Will it try to rise up? Will it try to sink down? Or will it be indifferent to the outside condition and will it stay where it is? What do you think? Okay, good, very good. Warm air naturally tends to rise up. That is what we have looked at it. And cold air, simultaneously, we have seen, tries to sink down. Now, let us associate that with the conditions of pressure. So here, think about it let's suppose here, this is the ground surface. Okay. Now, let's name this scenario as A, B, and C. So, let's suppose in the case of B, the ground surface has been heated up. Let's suppose the ground surface has been heated up. Now, as it is heated up, it will heat up the air column and the air parcel above it as well due to conduction. That will be heated up. Now, this air parcel or any sample of air, this will get lighter. It will try to rise up. Now, imagine if this is the ground surface, here the air is rising up, right? So, what will be the impact on pressure which is experienced on my hand? Ideally, this was the air which was there, but now the air is rising up. So, the impact of pressure on my hand will be reduced. So, rising air column always creates a low pressure. Keep that in mind. Regardless of whatever the conditions might be, regardless of whatever the causes might be, the causes can be wind movement, causes can be temperature. Whenever we come across a rising air parcel or a rising air column, that will always end up exhibiting a low pressure. Okay? And this stands true for all different types of pressure created. Rising air parcel or rising air creates a low pressure. Whereas, if in an area, let's suppose we consider A. Now here, let's suppose A is situated at the polar region, around the poles, in Antarctica, let's suppose. Now in Antarctica, even if I wake you up in the middle of the night and I ask you this simple question, that what do you think will be the temperature in Antarctica right now? I'm sure, other than obviously hurling abuses, other than that, I'm sure none of you will be confused by the fact that whether Antarctica is cold or whether Antarctica is hot. We all will know that polar regions are always very cold, especially the regions around Antarctica, Arctic. They are very, very cold in general. So let's suppose we talk about Antarctica. The temperature is very cold. Now there, the air will be also very cold above it. Now this air, being cold, will have a sinking tendency because colder air tends to become heavier, and that heavier air will tend to sink, and that will create a kind of a pressure. So always sinking air column, wherever it is, imagine if the air right now is like this, and if there is more air which sinks here, what will be the impact of pressure on my hand? The pressure will increase. So always sinking air column or sinking air is associated with high pressure. Always. So you have a region of low pressure. You also have a region of high pressure. Now, in between low pressure and high pressure, is there any interaction which will happen? If yes, why? So understand it in the very simple terms of the particle movement. Yesterday also I told you, for any concept, attack the basic portion of how the particles will behave. So imagine if this portion B, this is warmer, or let's consider here, okay, B, this is warmer. And here, the air is trying to rise up. Now, as the air is trying to rise up, here at the ground surface, for a temporary moment and a temporary duration itself, but at the ground surface, it will create a kind of a vacancy of sorts, a kind of a gap in terms of air particles because the air particles are rising up. So the surrounding regions will try to fill that gap. and fill that vacancy. And here you observe the excessive amount of air particles in surplus. So at one place you have something in surplus, at one place you have something in deficiency. Natural tendency is for the surplus items to move towards the deficient areas. So natural tendency will be that the air particles from here, they will try to rush in to fulfill that gap, right? To fulfill that gap created due to rising air. Now that is that rushing motion that you will observe of the air particles which are in surplus to a region where they are in deficit. So that rushing movement that you will come across, that is what we refer to as wind. So when you come across or when you encounter wind in any area, in any place, always understand it is moving towards a low pressure region. Winds will always blow from a high to a low. Remember this. Winds will always blow from a high pressure to a low pressure area. So whenever, let's say, you are encountering a wind and the wind is moving across your face, so always understand somewhere behind you, you have a condition of low pressure, and somewhere in front of you, you have a condition of high pressure where the winds are moving from. So that is where you have from a surplus region to a deficient region, the movement of air particles, which is significantly experienced. Now, oftentimes, this gives rise to a larger circulation also. If you take a look at the larger circulation that is initiated, you will observe that it almost covers the entirety of the troposphere in many of the situations. How and why? So here, let's consider, we'll come to the image later on. So before that, I understand when there is an image on screen, there is a lot of distraction going on. But try to understand a particular region, let's say which gets very warm or very heated up, right? And a subsequent area B, which is colder. Okay? Now, think about it. Not necessarily colder also. Let's assume it has got no particular inclination. It is neutral. Let's suppose it has got no particular inclination to declare itself as low pressure or high pressure or high temperature or low temperature as of now. It wants to stay neutral. Wait for the results. Now, here, when we talk about A, let's suppose A is heated up. Now that A will heat up the air above it by conduction. Now, once the air above it is heated up, it will start becoming lighter. Why will it become lighter? Because the air particles, they will gain energy due to the heat. So the air particles will be moving in absolute random directions. And the air particle will even try to escape from this particular air parcel or the volume that we are considering. So that is why it will become lighter and it rises up. So anything which rises up, will it rise up till eternity? Never. Anything which rises up will rise up only as long as that air is still lighter as compared to the surrounding. That is a very basic fundamental, isn't it? Even when you take a look at the balloons that you get in the fair and the various different celebratory fairs in all those places, you will find that even those balloons, you leave it up. Is it, have you ever come across a scenario there where someone has told you that I released a balloon 2 years ago and today that balloon has reached moon or today the balloon has reached Mars? Never. The balloon will rise up only to an extent. Beyond that, it is your ambition which will rise up. Beyond that, the balloon will never rise up. Why does the balloon not rise up beyond a point? Because it is not lighter anymore. And why will it rise up at the ground surface? Because there is a low pressure inside. It makes it lighter. It will shoot up. So the air will rise up as long as it is warmer than the surroundings. Why? Because as long as it is warmer than the surroundings, it will always be lighter than the surrounding air. So the air tends to rise up. Now, as it rises up, it will tend to expand, isn't it? Because it is moving into area of low air density. So air density is maximum where? Closer to the ground surface. This is where the air density is maximum. Density of air is maximum at the ground surface. Now, as it rises up, it is going to go into an area where the air density is low. So what will be the natural tendency of the air parcel? How will it behave? It will tend to expand. Wherever it finds a space, it will expand. So there will be adiabatic cooling. Naturally, it will expand. Adiabatic cooling. Meanwhile, in the surrounding air, here, and so on, in the surrounding area, here also the temperature will reduce. But by what factor? By the normal lapse rate, or by the dry lapse rate, or the moist lapse rate, depending upon the atmospheric scenario and the region of the planet that we are in. So let's suppose here the temperature of air has fallen by 5 degrees Celsius, but the temperature around has dropped by around 10 degrees Celsius due to dry lapse rate. Air will still be warmer, it will continue to rise up. It will rise up till where? It will rise up as long as the temperature around it is lower. That is up till the region of tropopause. Because beyond tropopause, you start getting hotter air, warmer air. So this air parcel which is rising up would have cooled down sufficiently by the time it reaches stratosphere. So it will rise up till tropopause. Okay? And here, as the air is rising up, it will lose temperature. It will cool down in the process. It becomes very, very cold eventually. And by the time it reaches tropopause, it becomes very cold, sufficiently cold. Let's say the air temperature is minus 20, minus 30, minus 40 degrees Celsius. But the surrounding air is, let's say, around minus 45 or minus 50 degrees Celsius. So that is why it will rise up till tropopause. Once it hits tropopause, generally it cannot rise above it. Because in stratosphere, again, you have warmer air. So if you have to imagine it, think about it, this is the surface, right? This is, let's suppose, troposphere. This is stratosphere. Stratosphere. Here, the air will rise up. The air gets cooler. Cold air. And here you again have a section of warm air. So the warm air parcel which is rising up will rise up only till this extent. Beyond that, it enters into a territory of warm air. Now think about any room that you are sitting in, whichever room that you are sitting, I hope that you are sitting. So whichever room that you are sitting in, imagine that room. Think of the ceiling of your room or the roof of your room to act as the tropopause. Now imagine that an air parcel is rising and it hits that ceiling. It cannot rise any further. Where will the air parcel go? Will it get disappointed that there is no point of all this effort? Let me fall down. At least I had more respect there. No, it cannot fall down, because subsequently after this more air would be rising, because this warm conditions would be feeding on to that rising air. So it cannot return back to its original position. Where will it go? It will diverge. It will move across. Right? Sometimes you would have seen that, let's say, when you light a fire or you light an incense stick, basically you would have observed that the smoke rises up, it hits the ceiling, and then it diverges, it moves across. So this air will also spread. It moves here. Some part of it will move here as well. But for consideration's sakes, let us consider only one section of it which is moving here. Now this air is spending some time at the topmost region of troposphere. The temperature is very, very low there, around -60, -70 degrees Celsius in general. Now the temperature being this low, the air will also become much colder. Slowly and steadily it will become colder, isn't it? Because eventually, when you stay in a particular area, you gain the property of that area. You attain the property of that particular region, right? So, as the air is staying in the topmost portion for a longer period of time, it will gain the property of that area. It will become very cold. And as long as it is at the same temperature as compared to the surrounding, it will stay there. But eventually, it will become colder, colder as it is moving. It will become much colder. Eventually, when it becomes slightly more colder than the surrounding, it becomes heavier. And when it becomes heavier, let's suppose it becomes heavy here. Here, the temperature drops sufficiently. So, immediately, the air will initiate a sinking motion. It will start to sink. Now, as it starts sinking, understand that the air will slightly be compressed. Compressed because of adiabatic compression. It is moving into a region of maximum air density. So the air will compress ever so slightly. Nonetheless, it continues its move and it continues to move here. And then it hits the ground surface. Now, here, when it hits the ground surface, let's take this position as B. Now, when it is hitting the ground surface, that will create what conditions at B? What pressure conditions? The air is sinking at the region of the ground surface. So it will exert a pressure on the ground surface. So B will experience high pressure. And after hitting the ground surface, will the air finally rest that now my work is done, now let's retire from service? No. Imagine again, if you have, let's say, a portable air cooler or a table fan, if you blow that table fan or a portable table, the small ones, the Chinese ones that you get, the small ones. So if you blow it on the table and after the air hits the table, where does the air go? Does the air come bounce back like a tennis ball? No, the air will diverge, the air will spread. So here also, this air will spread. Eventually, it will seek to fulfill any vacancy created in the nearby region. And here the vacancy is created by the rising air, creating a low pressure. Now, you can extract multiple pointers from this. The first pointer that you can extract is that, look, wherever you have significant amount of heating, if in case other conditions are not prevalent, temperature dependent pressure, if you have significant amount of heating, air will tend to rise up. It will rise up till the region of tropopause generally, right? Now, as long as it doesn't cool down in the tropopause, it is not falling down. The moment it cools down, that is the moment it will start falling. And it falls wherever it is falling. Here, this B, we have not considered what is the temperature at B. When we were talking about the creation of high pressure at B, if you recall, we have not talked about that B is going to experience a high temperature or a low temperature. It doesn't matter. Here, a high pressure is created because the wind is sinking down, because the wind naturally or the air naturally is sinking down. So here, the high pressure which is created is independent of temperature. Independent of temperature. Let's suppose at B there is a temperature of 35 degrees Celsius. Let's suppose B is experiencing a 35 degrees Celsius temperature. But does not mean this air has cooled down at this high temperature, at this high elevation. It has decided to sink. Does not mean that this wind will realize, okay, I have chosen a wrong destination, take a left turn, I have to go somewhere else because B is very warm, I need to go to Shimla. No, that is not the case. There, the sinking air has been sinking from the very top level. So that is where, regardless of the temperature, it will sink there because air starts sinking. Air starts to sink when it becomes very cold. Now, while it is sinking, it will experience adiabatic compression. So here, this air will experience adiabatic compression along the way. It will warm up a bit as well. But again, it is warming up but falling on the ground surface. So if any cold thing falls on the ground surface, if any warm thing falls on a ground surface, if something falls on a ground surface where they don't tell you what is the temperature, regardless of anything, sinking air column always will experience or will exhibit a higher pressure. So its temperature will rise up ever so slightly while it is falling, but then still it will exert that pressure. And that is where on B, it will create high pressure conditions, and that is how the circulation is achieved. Overall, you will observe this is the circulation where in the low pressure, air warms up, rises, and then eventually there's a circulation. Air will fall down only when it is colder. When it is colder, it will start falling down, it will fall down, it will create a high pressure on the ground surface. Is this portion understood? Let me know. Nitin, why adiabatic doesn't take place when it sinks? I told you adiabatic compression will take place here, Nitin. It will take place. Some amount of adiabatic heating will take place. But just because the air becomes warmer while it is sinking doesn't mean that it has become warmer. Then rather than sinking, it will now start rising up, that I have got more fuel, now I can drive more. No, it is warmer, still it has a sinking column associated, so it will fall on the ground surface. Okay? Can you please explicit? Can I explicit about what? Shubhajit, please let me know. What do you want me to be explicit about? Will high pressure happen in plain land or only in hilly areas? It can happen anywhere. It can happen in polar regions, it can happen in plain areas, it can happen in hilly areas in general. At high temperature, at high pressure, very little amount of air to rise up. Correct, Pranay. Abhijit, it still sinks because it is still colder than the surrounding. Yes. As long as it is colder than the surrounding, it will continue to sink. Sometimes there are other factors involved as well. We will study later on. Sometimes just because there's a movement in the upper air, which imagine that there is a wind, right, in your portable table fan, which is continuously pulling that or pushing that amount of energy on the ground. Now, regardless if you are heating it on the ground as well, still, as long as that table fan will operate, it will continue to push the air. So there are multiple factors which drive the sinking of air. Can you please explain independent of temperature point, Shubhajit? Okay. And Subhash, while raising, so this air parcel positive lapse rate differs with the air around the parcel. Yes. So here, the air parcel, Shubhajit, which is rising up, understand, it will expand ever so slightly, and that is where it will lose the temperature. Now the surrounding conditions, they will observe either the normal lapse rate, moist lapse rate, or dry lapse rate, depending upon what is the moisture condition. So the surrounding, let's suppose ground surface is 40 degrees Celsius. This air cools down to around, after rising for some distance, let's say it cools down to be around 33 or 34 degrees Celsius, right? Let's suppose by this time the surrounding air temperature is 30 degrees Celsius. So this is still warm, still will continue to rise up. Okay. So Shubhajit, your question was about the independent of temperature. Understand again, here observe, when we talk about and look at the upper portion in the region of troposphere. So here the air has decided to sink when? Air has decided to sink either by has the air decided to sink by looking at the ground surface, that B is good, A is not bad, we can go to C also, C has got lot of crowd, let's go to an offbeat location, we will have more fun. Has the air decided based on these criteria? No. Air has decided to sink. Why? Because it has become very, very cold. It is not dependent upon the where it is sinking. It has become cold, it has to sink. So here it is sinking and it will create a high pressure at B. Now B can have any temperature condition. B can have low temperature, B can have high temperature as well. But it is sinking there. So that is why the high pressure created at B oftentimes is independent of temperature. But at the same, in certain cases, it is temperature driven as well. Okay. If high pressure exerts in a region, does it affect the people living in that region? Yes. It is. It will not bring rainfall. It is meant with the absence of rainfall, and there you will observe lack of any cloud, clear sky, and over a longer period of time, it can create oppressive weather conditions as well. Shubhajit, is that understood? Please let me know. And Abhishek, is it also the reason for movement of cloud? Movement of cloud is determined by the wind movement in the upper atmosphere. So yes, if let's say you have a cloud here and that cloud comes in the way of this, it will also experience a movement. So I hope this is the portion which is understood, that how circulation happens. We will study more about this. We will understand more about this. Don't worry. Yes, Vishal. See, for measuring pressure, what is done is a typical barometer is taken. In barometer, you have a mercury column. So the weight imposed by the air, that weight is basically imposed on a liquid mercury column. And as a result of that, let's suppose a typical barometer will be very similar in construction to somewhat like this, where you have a tube and the tube will have markings. Okay, this will be filled with mercury. Here the tube will have markings. Now the pressure exerted by, this is the mercury column, the pressure exerted by the air above, that will push the mercury to rise. So the amount of mercury rise that is experienced, that indicates to you whether there is a high pressure or a low pressure. Okay. Now we come to the different types of pressure zones, thermal and the dynamic pressure zones. So what are these? So what do we understand by a thermal pressure zone? What do we understand by a dynamic pressure zone? So here, thermal, the name in itself, what does it tell you? Something to do with temperature conditions, something determined and driven by temperature realities. Dynamic, something which is not static, something which is consistently in motion. So, as I told you earlier itself, if you recall, pressure can be determined either by temperature or pressure can be influenced by movement of air as well. So, when we talk about a dynamic pressure zone, in this case, conditions of rising air and sinking air are created due to movement of winds. How? Let's understand that. How is it that a movement of air will induce rising air column or a sinking air column? So here, again, I will take the example of the same room that you are sitting in. Again, I hope that you are sitting as of now. So here, let's consider this is the room that you are sitting in. Okay? Let's have a bigger room. Now, here, let's suppose, because you have complained that there is a lot of heat, I cannot study in this much hot conditions, I need cooler conditions, otherwise later on don't blame me that you did not clear civil services. So what your parents have done is, they have, or your guardian, what they have done is, they have installed lot of fans there, coolers, large scale blowers. So let's suppose you have a lot of fans installed here, here also, in this end also. Now, this will initiate a wind motion in your room itself, closer to the floor. It will initiate the movement of the wind. The wind will be moving here. From here also wind will be moving. Now this will converge at a point. This will collide at a point. After that, where will the air go? Does the air have any other place that, okay, now we are done with this room is very boring, I will go out through somewhere and I will go to the other room and chill out? Does the air have that option? No. So what will the air do? Will the air cross each other and attack the other fans, that I have come from this fan, so I will go to the other fan, that is my destiny, that is my fate? No. Here, the air will basically collide. It will have a surplus in this region. And because consequently and continuously more air is being pushed into the region, at the central portion, the air will have no other option but to rise up. It will rise up. It will hit the ceiling. And here, think about it. Till when will it rise up? As long as these fans will operate, as long as this air will continue to move, it will continue to rise up. Then it will hit the ceiling. And when it hits the ceiling, again, it cannot break the ceiling and go up. It doesn't have that much power. So there, the air will spread and diverge. So at the ground surface, what will be in this region? In this region A, what will be the condition of pressure? At that region of A, air is coming together, there is a collision, there is a rising up. So because the air is rising up, anywhere where you have a rising air column, you will have a condition of low pressure. Now think about it. In this entirety of the discussion that we have had for the past 5 minutes, have we even for once talked about what is the temperature at A? What is the temperature at the region of the fans? What is the temperature at the ceiling? Have we talked about temperature at all? Absolutely not. So this rising air column was created. Why? Because of convergence of winds. When the winds are converging, eventually they are pushed up and they rise up. So here, convergence creates of winds forces them to rise up. So, can we not say that wherever you will come across a convergence of wind, that will induce a low pressure in the region. Can we say this? That wherever you have convergence of wind, it will create a kind of a low pressure there. We can talk about it, isn't it? Then imagine the other circumstance. Again, you are sitting in a room, okay? And this time, as a joke, what your parents have done is, you have complained that it is very warm, very hot. What they have done is, they have installed fans higher up. That you asked for fans, you did not tell me the location, so I've installed fans in this area. Now that means this time the air will be circulated, or the air will be supplied here in this region, right? And the air will continue to flow. Now here also the air will converge. Where will the air go after that? When they are converging, will they rise up? That, see, I did the same thing at the ground surface, I could rise up. Here also I want to rise up. No, they cannot break the ceiling. So where will they go? They will eventually drop down. They will drop down here. When they drop down, they will drop down to the floor. And after that, they will spread again. Isn't it? Now, in this particular place, let's say B. Here, have we talked about that? What is the temperature at B? Why is it that the air chose that I will drop only at B, I will not drop close to B or here or there? No. Wherever the convergence has happened, there itself it has dropped down, right? So here at B, what is the pressure condition that you will have? You will have a high pressure. Good, very good. Okay, so can we not say that here convergence, or rather, if we talk about the ground surface, here in the ground surface, what is happening as the air is sinking? It is diverging. So here we can talk about divergence at the ground surface, divergence of air at the ground surface, or we can say convergence of air in the upper atmosphere, in the upper region. So convergence of winds in upper atmosphere creates divergence on ground. And when you have divergence created on the ground surface, what will it induce? It induces high pressure. So here, low pressure and high pressure conditions, they are created due to wind motion itself, not at all determined by temperature. So this particular dynamic pressure zone, this overall you will find is independent of temperature on the ground surface. We experience this in India. In the northern part of the country, we experience this kind of a high pressure created purely because of the movement of the wind, not at all determined and not at all dependent on the temperature. That is why in northern part of the country, you will specially experience, even if there is a very high temperature, there is no rainfall for majority of the year. That is why when there is rainfall, people get so excited and so surprised that North India is experiencing rains. What will happen next? Will we experience flower petals showering from the sky or what? So rains are very rare. Rains are not very regular in the northern part of the country. And one of the reasons is this particular factor of creation of divergence on the ground. We'll talk about it when we talk about the wind types. Then we come to the thermal pressure zones. Now, thermal pressure zones here, they are conditions of rising and sinking air are created due to impact of temperature on ground. The ground surface, the impact of temperature, in the sense that, let's suppose, if an area is very hot, if a region, let's suppose, is very hot, significantly warm. Now, what we have discussed is that the air above it will also get very hot, right? And this air gets warmer, becomes lighter, and when it becomes lighter, it will rise up. It will start to rise up, isn't it? So, warmer regions can experience rising air. So, warmer regions will experience low pressure. But it is not something written in a gospel, or it is not something carved in a stone. In warmer areas, you can also experience this condition and a condition of high pressure. So it is not something that is absolutely written by the nature of the law, and God himself came down and wrote this, that look, this is warm region, there is no other alternative, you have to have low pressure. No. Warm regions experience low pressure under normal conditions. But in atmospheric area, or under the climatology aspect, you always have to consider that normal conditions prevail for a brief duration, or normal conditions are always intervened by other factors. Right? For example, when you are preparing for civil services, you can have that under normal conditions, I study for 5 hours. But that never happens, does it? Some or the other emergency will come. The prime minister has called me. I have so many meetings. You don't know, I have this much amount of busy life schedule. I don't know how I am taking out time. My friend, such an emergency it was. He had called me for a cup of tea and I could not ignore, so I missed out the studies. So never will you find a normal condition to be prevalent. Similar is the case in climatology as well. Rarely will you find in atmosphere that every conditions are normal and conducive enough. So that is why under normal conditions, warmer region will have a low pressure. Then under conditions where, let's say, this region is very cold, so air will become cold above it, air will sink. So air is colder, and that colder air means heavier. That will create high pressure. Very similar to what we started the discussion with. So colder regions they exhibit high pressure. Okay. Now, why the air is flowing from low pressure zone to high pressure zone? Where is the air flowing from low pressure zone to high pressure zone? Wind always flows from high to low pressure. Yes, wind will always move from high pressure to low pressure. Where did you see that the air is moving from low pressure to high pressure zone? Please point it out. In dynamic pressure. Okay. In dynamic pressure, where is that we have indicated? In dynamic pressure, in the scenario 1 and scenario 2, both of them are independent of each other. Here we have not even discussed that where there is a low pressure, where there is a high pressure in each of the regions. Is there an issue in understanding the dynamic pressure zone? Kindly let me know. See, I will very quickly recap it. In the portion of the dynamic pressure zone, see, the air, when it is colliding and converging on the ground from two areas, if the air is moving, it is converging on the ground. Why will from two areas air will converge? Because there must be surplus on both the regions. That is why the air is coming. So when the air is coming from two high pressure regions, let's suppose it converges here, it has no other place but to rise up. So as it is rising up on the ground, it will create a kind of a low pressure. Conversely, in a region, let's suppose in the upper area or in the region of troposphere, the air is converging and colliding. Now the air has got no other place to go. It will sink and it will create a high pressure condition on the ground surface. So that is the sinking air creating that. In box 2, the upper side is low pressure zone. Okay, but the ground is high pressure zone. So in that aspect, imagine here, if the air is moving, where will the air go, my dear friend? Leave the entire concept of low pressure and high pressure for a brief moment. Where will the air go if it is converging here in this region? What can you think about the possible reason for the air? Will the air stop moving? That no, because somebody told me I cannot move in that region, so I will not go. Does the air have that kind of a choice? Think about it in terms of air also behaves like a fluid, like a liquid. So fluid dynamics, if you think about it, then where will that fluidic air go? Will the air go in the stratosphere then? No, stratosphere is warmer. Air cannot rise in the stratosphere. So where will this air go? It has no other place to go than to sink down, isn't it? So that is the basic concept even here when you talk about it, that air is falling from the region of troposphere to the region of the ground. Ground has high pressure, troposphere has comparatively low pressure. So why is the air moving in terms of low pressure to high pressure here? Understand, when I talked about that air moves from high pressure to low pressure, this is about the ground surface. On the ground surface, wherever the air will initiate any motion, it will always be from a high pressure to a low pressure. But if that would have been the condition, colder air from above will never have come down, because always the ground surface will have higher pressure as compared to the upper region. Why it sinks? Here it is sinking because it has become very cold. It has got no other place to go. So that is why it is sinking. Here again it is sinking. Why? Because it has no other place to go. It is converging and it has to drop down. Right? So that is why it is creating a kind of a high pressure on the ground surface. Now after this, we come to the aspect of isobars. Now, just like the case of isotherms, in the case of isotherms, we studied what? What are isotherms? Isotherms basically are the lines which connect places exhibiting or indicating same temperature. When we talk about isobars, these end up joining places of equal atmospheric pressure. Each and every place will have different pressure, maybe on a daily basis, maybe on a weekly basis, definitely on a seasonal basis. So isobars, let's suppose you consider the isobars across the country, India. So here, if you observe any of these isobars, observe this isobar. Here you will find what is written here, 998. So any place which lies on this isobar would obviously end up indicating 998 millibar of pressure. Observe this isobar here. Or why to observe that isobar when we can observe something else? Observe this particular isobar here. Now this is where you will find written 1004. Okay. So a very normal kind of logic here. Here, comparatively, if I consider this isobar as A, consider this isobar as B, please don't commit mistake in this. It will be like heartbreaking. Okay, on a Sunday, I don't want early in the morning to have the heart broken to such an extent. If I ask between A and B, which is the low pressure and which is the high pressure, please let me know. Okay, thank you. Very good. B is high, A is low. Hajra, in dynamic pressure, it is independent of factor if air is warm or cold? Yes, in many of the cases. Okay, good. Thank you. So here, B is comparatively a high pressure, A is a low pressure. So the wind movement always from a high to a low, always. Wind will blow on a surface always from a high pressure to a low pressure. Wind will blow from here till here. Can we say this? Wind will blow from a region of high pressure to a low pressure. It is a different matter altogether that even in this region of B, the wind will come. Here, observe, you have 1007. So if I consider C, C is comparatively a high pressure as compared to B. So here the winds will supply this. Now, these winds are coming from B to A. They are coming from the region of Bay of Bengal. And when they are coming from Bay of Bengal, they will pick up the gifts. What are the gifts there? So from Bay of Bengal, they will pick up moisture. And when they have picked up moisture, they come to the land, they will drop that moisture in the form of rainfall. That is why that region will receive rainfall. Okay, so this is one of the reasons why you receive rainfall. Now, all of this we get to understand how? By looking at the isobars, by looking at the isobaric presence in different areas. So isobars overall are those particular lines which indicate places exhibiting same pressure. Now let me ask you the same question I asked you yesterday. Can isobars cross each other? Can they crisscross each other? Okay, very good. Isobars will never cross each other. Just like the case of isotherms, they will never cross each other. Okay, so isobars never. Good. That means yesterday's portions are understood, and that is a good sign. That means today's portion will be easier to understand. They never cross each other. Okay, they will never crisscross each other, because if they do, that means one particular place at the conjunction will be exhibiting two different pressure points at the same time, which is impossible. Now here, the placement of isobars, when you are drawing the isobars. Now, these isobars, let's suppose I give you two conditions. Let's suppose I paint two scenarios in front of you. In both these, I am exhibiting a distance of 100 kilometers between the two ends. Okay. Now here, if I am drawing the isobars, in the first one, let's say the isobars, each indicating a 1 millibar, that is, let's suppose this is 1010, the other will be 1009, and so on. Okay. Now, in the first one, this is how the isobars are. Okay. And in the second one, each again indicating a 1 millibar drop. Let's suppose this is the isobaric representation in the second scenario. Now, if I consider this place as A, this place as B, this place as C, and this place as D. Now here, out of A to B or C to D, in which of them, just by application of logic, in which of them do you think that the pressure drop is more sharp by the time that you reach the destination? While you are moving from C to D or while you are moving from A to B? Where do you think that pressure drop will be very significant? Correct? Okay. See, each of the isobars, they indicate 1 millibar of drop. So if this is 1020, this will be 1019, this will be 1018. Okay. Okay. Good. So in this case, the pressure drop will be much more drastic when you are moving from A to B. Why? Look at this. Suppose 1009, 08, 07, 06, 05, 04, 3, 02, 01, 1000, then 999, 998, 97, 96, 95, 94. So from 1010, the pressure has dropped to 994 millibar. Whereas in this situation, from 1020, it has dropped to 1018 millibar. So what does that mean? That means the pressure drop is more drastic in the first case as compared to the second scenario. Now, what can we conclude from there? Can we not conclude that if the isobars are very closely placed to each other, that means the pressure is dropping rapidly over a distance? If the isobars are distant from each other, that means the pressure is falling at a very gradual rate. Isn't it? We can say that. So here, if isobars are very close to each other, that means what? Pressure changes drastically. This change of pressure over a distance, can we refer to it as gradient of pressure? Can we refer to it as gradient of pressure? Change of pressure over a distance. It can be referred to as gradient of pressure or pressure gradient, isn't it? So if isobars are very close to each other, the gradient is high, the change is very high. We can say that. Then, if isobars are far from each other, isobars are far from each other, gradient, that is the pressure change or the pressure drop, pressure gradient is very low. In this case, pressure gradient is high. Pressure gradient is high. Now, what do we accomplish by knowing that if the pressure gradient is high or low? What is the benefit of knowing that? That the pressure gradient is high or the pressure gradient is low? Why should we know that at all? That is important in terms of movement of wind. So here, when we talk about pressure gradient, it is the change in pressure with horizontal distance, right? The change in pressure with horizontal distance, how the pressure is changing, that is pressure gradient. We do know that winds will always blow from a high to a low. But how high and how low? Let's suppose I again give you two scenarios. Let's suppose I give you a scenario A, where the wind is moving from a place 1020 millibar to a place 990 millibar. Even though very rare to find this, but still, let's suppose this is the wind movement. And in B, I give you a scenario where the wind is moving from 1010 millibar to 1008 millibar. So out of A and B, where do you think the wind motion will be very fast? In the region of A or in the region of B? What do you think? Where do you think the movement of air will be very fast? Okay. Anybody who thinks that in B, the wind movement will be very fast? Okay. So all of you have, most of you, other than a couple of you, most of you have given the correct answer. The distance is the same. Distance is same. So here you will observe that the pressure difference in this region, pressure difference or pressure gradient, that is the change in pressure, in this case is very high. Now, how is that important? So think about it in terms of liquid. Let's suppose you consider water. Now, if you consider water, let's suppose you have a glass in hand and with a jug in your hand or a jar in your hand, you are pouring water in the glass. The water will have a flow. It will have a velocity. Now, suppose you climb up to the third floor and from the balcony, then you are pouring the same jar of water on the ground floor. Now, obviously, when you are standing on the third floor, you will have a greater velocity of water. Why? Because there is a height gradient in terms of movement of water. Similarly, in terms of movement of wind, pressure gradient is a determining factor. Greater the pressure gradient or greater the change in pressure means more winds will be pushed towards that particular area. More powerful winds will be pushed if the gradient is high. So this pressure gradient, overall observe, a region has got a high pressure. High pressure means excessive materials on the ground surface. That is what is indicated by high pressure, right? Low pressure, very little particles on the ground surface. Always the wind will try to blow from high to a low, always from a surplus region to a deficit region. Now, if suppose here you have much more particles, let's suppose if I add much more particles here, and if I somehow am able to remove few of the particles from here, there will be greater vacancy in the region of low pressure and a greater surplus in the region of high pressure. So more winds will blow, more particles will blow. So higher the gradient, greater is the movement of the pressure of the wind. Okay, so greater the difference in pressure, means what? Higher or greater is the air flow, means stronger winds. So we can say that high pressure gradient will mean stronger winds and vice versa. and vice versa will also be true. That is, if you have a low pressure gradient, you will have weaker winds. Okay? Farthest the gap, higher is the wind pressure. Not the gap, Utkarsh, the difference in pressure. If greater difference in pressure, greater is the wind movement. Pranay, can we make analogy that we see in geomorphology? Higher the gradient, higher the... Yes, absolutely. That is the same thing. Vice versa means the opposite is true. Okay. I don't want you to confuse in English here. So, low pressure gradient means very weak winds. Okay, right? So, is that clear, or anybody having any doubt up till now? Let me know. Clear? Good. So now we move on to the area of the factors affecting the wind and the movement of wind and the movement of air. But we'll do that after we take a break. So we'll take a break right now. We'll take a 15 minutes break, the first break of the day. So we'll take it up for 15 minutes. We'll be back in 15 minutes. And then we will continue with the portion of Coriolis force. That is important to be understood. And then we will also take a look at the permanent wind system. Okay. And is there any method to get isobars, as it will keep on changing? You can follow it on the the Indian Meteorological Department's website. They always keep on updating the isobars on a daily basis. Okay. So let's take a break and let's be back in 15 minutes. A confirmation for the audio, please. If the audio is clear and available, kindly confirm the same. Thank you. So now, after this, we come to the portion of the factors which influence the velocity and the direction of the wind. And here, why do we say velocity and direction of the wind? Because you would also have experienced in your day-to-day life that when you experience wind movement overall, it is never the same. Sometimes the winds are stronger, sometimes the wind appears to be coming from a different direction, sometimes the wind appears to be coming in different direction with a slower speed, with a faster speed, and so on. So the wind velocity and what is the momentum that the wind carries, what is the velocity with which the wind is moving, if it is a strong wind, if it is a weaker wind, if the wind is moving in a right to left or left to right direction, that is basically determined by a host of various factors. So what are those factors? So overall, you have to understand that the gravitational force is always significantly active, and that is what keeps the wind stuck to the ground surface, because the gravitational force is particularly active here. Other than that, you have three important components and three important forces which continue to act, and they are the pressure gradient force, the frictional force, and the Coriolis force. Now, these three forces overall, they can be contributed or they can be thought to be the main determinant which leads to the wind motion or the wind movement in any particular part. So one by one, we shall be covering what do we understand by the pressure gradient force, what do we understand by the Coriolis force, and what do we understand by the frictional force which is exerted. Now we have already seen what do we understand by pressure gradient. That is the difference in pressure from one region to another. That is referred to as pressure gradient. That is the difference. So if the pressure gradient is stronger, the wind movement will be stronger. If the pressure gradient is low, the wind movement will be low. So if we take a look at the pressure gradient force, the rate at which the pressure is changing with respect to the distance, that is referred to as pressure gradient. Now, this pressure gradient is very important to initiate the wind motion. So, this pressure gradient initiates the wind motion, initiates the motion or the movement of the wind. That is, if there is no difference in pressure, no wind movement will happen, regardless of whatever other factors are at play. There has to be a pressure gradient. And we have seen that when the pressure gradient is stronger, wind will be stronger, lower, wind will be lower. And how do we get to know what is the pressure gradient? We get to know that with the help of the spacing of the isobars. If the isobars are closely spaced, pressure gradient is high. If the isobars, they are distant from each other, the pressure gradient is low. So here, if you think about it, let's consider the region of North America here, indicated and dotted with the various isobars. Now, if you observe here, you have the high pressure, absolute high pressure here, where the pressure is around 1036 millibar, as high as 1036 millibar. And the absolute low pressure, observe 988 millibar. So the wind will blow from a high to a low. Always keep that in mind, never forget that. So here, if you will observe, the spacing of the isobars will give us an idea about the pressure gradient. So if I consider this particular stretch of landmass, what can I say about the pressure gradient here? Just by looking at the spacing of the isobars. Here, do you think the pressure gradient is high or do you think the pressure gradient is low? What do you think in this case? Very good. Pressure gradient is low. Beautiful. Pressure gradient is low here. It is significantly low. And in this portion, you will find that the pressure gradient is very high. Pressure gradient is high. So the winds which are going to initiate the motion due to difference in pressure, the winds initially will be moving at a slow speed, because the pressure gradient is slow means the pressure gradient is low means the winds will be slower. So you will have weaker wind movement. And whenever the pressure changes quite drastically in a small time duration or in a small distance, that basically means you will observe or come across a strong wind movement. So this is the initiator of wind motion, and this is what leads to the wind to move in the first place. After this, here, this is one of the forces or one of the factors, and this factor is important for the initiation. But once the wind is in motion, then there are other factors at play as well. For example, here you have the Coriolis force. Now, Coriolis force is referred to as an apparent force. Apparent force means it is only going to act on any object which is moving independent of the surface. It is any object which is moving independent of the surface, they will experience this Coriolis force. And here you have to understand that this particular Coriolis force, this will be in action only because the earth is rotating. The earth is spherical and it is rotating. That is why. Now, why is it that it will lead to a Coriolis force? That is because you have to understand that different places across the planet, they have a different rotational speed. Remember what we studied in the first module, in the first session. We studied about the fact that as the planet is rotating around its axis, different places, they will exhibit a different speed of rotation, right? If I name this A, B, C, and D, and if I were to ask you, I will launch a poll for this to get a better idea. So if I ask you, and I want everyone to answer, I want everyone to reply. I get to know how many of you don't reply, so I want everyone to reply here. If I were to ask you, out of A, B, C, and D, where is it that the speed of rotation will be the slowest? Out of A, B, C, and D, where is it that the speed of rotation is the slowest? What do you think? Let me know. Speed of rotation is the slowest out of which of these places? Good. Majority of you have given the correct answer. Here, the speed of rotation will be slowest at the region of the poles. Here. Why? Because how do we get to measure the speed? Speed is equal to distance by time. Yes, that is the ironical part, Jay, that the answer is given in the image. Still, many of you manage to give the incorrect answer. And that is where you should have a pat on your back for this, that it is something which is very depicted in the image itself. But still, all of you have managed to give the incorrect answer in this. You should pat yourself, go in front of the mirror and pat yourself on the back for a couple of moments. A slow clap is needed for yourself. But nonetheless, let us try to understand the concept of it. This concept we have covered in the first module itself, but I'm assuming that most of us, we have forgotten that. because we have not taken a look at all of these. We are waiting for some fine day when the stars will align, the sun, the moon, and the stars, all of them will be visible to us at the same time. There will be a heavenly voice which will be heard that today you have to initiate the revision. Then we will initiate the revision. So with that assumption, let us assume that you have forgotten all of it. So starting from the very basics, speed is equal to distance by time, distance traveled by time. Now this place A, what is the distance that it will travel in one rotation, can be understood if we take the earth. Here, let's suppose this is the radius. Here in this area, if I were to consider the portion here, small r, here, let's consider places on A, B, and C here. Okay. Now, if you take a look at the distance traveled by A, what do you think will be the distance traveled by A? Distance by A in one rotation. In one complete rotation, the planet is continuously rotating from west to east. So in one complete rotation, distance traveled by A can be given by 2 pi r, right? Basically, the circumference, right? Distance traveled by B in one rotation will be 2 pi small r. What is the distance traveled by C in one rotation? As the planet rotates, does C move at all? In the case of A, it completes one larger distance. In case of B, a smaller distance. But what about C? C will not move at all. So distance covered by C in one rotation is 0. So if I have to find out, can I not say that because larger r, this r, is greater than smaller r, distance traveled by A is going to be greater than distance traveled by B, which is going to be much greater than distance traveled by C, which is equal to 0. I can say this. Now, here, basically, speed. So speed exhibited by A at this point will be distance traveled by A divided by, let's suppose time is fixed at 1 day. One rotation will take 1 day. Speed of B is equal to distance traveled by B by 1 day. And similarly, speed indicated at C is equal to distance traveled by C by 1 day. So can I not say in this, based on the above derivation, can I not say that speed of A will be significantly greater as compared to speed of B, which will be much greater as compared to speed of C, which is 0. So this takes us to the conclusion where we say speed of rotation is maximum at equator and decreases towards poles where the speed of rotation is 0. Rotation is 0. We can say this. I hope we don't have a doubt in this, that speed of rotation is going to be maximum at equator because that is where the maximum distance is covered, and speed of rotation will be 0 at poles because no distance is covered at the region of the poles, right? Now, this difference in velocity means if any object is moving from one area to another, it is going to move from an area of one particular speed of rotation to an area of a different speed of rotation. So this difference in speed of rotation at various places that induces a kind of a bending where the objects moving in the northern hemisphere, they bend to the right. Objects moving in the southern hemisphere, they bend to the left. And this bending, it is a result of what is referred to as Coriolis force. So as a consequence of Coriolis force, objects moving in the northern hemisphere, they will always bend to the right. Objects moving in the southern hemisphere will always bend to the left. And that is how you have the Coriolis force. Now, this would not have happened if, let's say, planet was a square or a cube, or let's say a cuboid. Then different places would have the same speed of rotation. But because it is spherical, that means different places have different areas that they cover, different distance that they cover, meaning that different places on the planet have different speeds. And when the object moves from one speed to another speed, there's a deviation associated. Why will there be a deviation? Let us understand that with the very famous car example overall. But before that, the key to Earth, the Coriolis effect lies in Earth's rotation. Specifically, Earth rotates faster at the equator than it does at the poles. Earth is wider at the equator, so to make a rotation in 124-hour period, equatorial regions race or move at nearly 1600 km per hour. Near the poles, the Earth's movement is almost 0 km per hour. So because of this difference in speed at different places, as the object moves from one region to another, it experiences a significant deviation. Let us take a look at that case. Let us consider that case with various examples. So we start with the first scenario. Here, we'll take the car example. So let's suppose I have a car and another car. Now let's suppose both of them are moving at the same speed. Let's suppose 30 km per hour. Both of them are moving at the same speed of 30 km per hour, let us assume. Now, when both of them are moving at the same speed, in this situation, let's suppose car A and car B. Now, someone from car A, now you would also recall it when you are moving on the road. Let's suppose someone else is moving in their bike or in their car at the same velocity as you are. So you will be able to see that car or that bike very clearly. And from your point of view, that those people will appear to be static, because as you are moving, they are also moving at the same speed, right? So from your relative point of view, they will appear to be static. So imagine if someone from A throws a ball to someone sitting at B. Now that ball will be caught, because both of them are moving at the same speed simultaneously. So that means if an object is moving in areas between same speed, they will be caught. There is no deviation overall, but we'll come to it. Here, let's consider another scenario. The second scenario. Let's consider the situation where car A and car B. Now let's suppose A is moving at 30 km per hour, B is moving at 130 km per hour. Now, repeat the same exercise. Someone from A throws a ball or chucks a ball towards B. Now, do you think the person sitting in B will be able to catch the ball as was the case in the first scenario? Do you think that by the time the ball reaches B, B would have moved ahead? Or do you think that by the time the ball reaches B, B would be still behind? What do you think? Obviously, by the time the ball is thrown and by the time the ball reaches here, B would have reached somewhere here. because B is moving at a much faster speed, right? Think about it. Road rage is very common in India, right? In any particular city, in any particular part of the country that you go, road rage is very famous. Road rage, as in the sense, short-tempered behavior due to the various traffic movements that you get. Someone crosses you at a blinding speed of 100, 120 kilometer per hour. You are moving at a sluggish speed of 22 kilometers or 3 kilometers per hour. Now, there, by the time that you will hurl an abuse or you will say something to the other person would have raced ahead, crossed the next signal as well, right? So, by the time the ball reaches B, B would have reached somewhere here. Now, if you ask a layman who is sitting there on the side of the road, watching everything go by, now that individual will tell you that the ball actually fell behind B, isn't it? That can be said that the ball will fall behind B. So here we can have our first conclusion. If an object moves from a faster speed or from a slower speed to a faster speed, the object falls behind. Okay, this can be one of the conclusions that we can make. Now we can make a conclusion about here also. If an object moves between the same speed areas, indicating same speed, the object is caught straight away by B. So that means there is no falling behind or falling ahead. So the object experiences no deviation. Then let's take another scenario. So here, let's suppose we consider A and we consider B. Now let's suppose A is moving at 100 kilometer per hour, whereas B is now moving at 20 kilometer per hour. Now someone from A, that person likes throwing balls out of the window. Let us assume that someone who is sitting in A, their favorite pastime is to throw balls out of the window. So this time also, someone from A throws the ball out of the window. Now in this case, what do you think? The ball, will it be caught by B? Will the B portion race ahead by the time the ball reaches there? No. This ball, when it is thrown from A, it will end up reaching a region where B has not reached as of yet. So this object will fall ahead of B. Why? Because A has got a velocity. So here we can say if an object moves from a faster speed to a slower speed, the object falls ahead. Okay, we have these three conclusions. 1, 2, and 3. These three conclusions, I hope they are understood. With the help of these three conclusions, let us try to understand the entire aspect across the planet and why there is a deviation, if at all, in between the different areas, and what is the deviation which is experienced rightward, leftward. Let us try to understand that. So for that, we take the planet, the larger planet. Now the planet is bulged around the region of equator. We know that the planet is slightly bulged around the region of equator, isn't it? Slightly above and below the equator also, the planet will indicate a similar radius overall. Let's assume this is the equator or 0 degree. Now, here let us consider a point A. Let us consider here a point B. Let us consider here point C. Now, here, when an object, let's suppose, is trying to move from B to A, in the sense any free object, not that you are driving your car, not that. Let's suppose an airplane is moving or a wind is moving, anything which is independent of the ground surface. A missile is being launched, anything. Now an object is moving from B to A. It wants to move from here directly. It wants to reach A. But can we say here what that the object is moving from a region of slower speed to a region of faster speed? Because this is where the speed is fastest, speed of rotation is fastest, of rotation is highest, and the speed of rotation decreases, speed reduces. Here also, as you go towards the poles, the speed reduces. So here, let's assume that an object is moving from B to A. It can be said that it is moving from a slower speed to a faster speed. What is the observation? If an object moves from slower speed to faster speed, the object falls behind, isn't it? So rather than reaching A, it will fall behind somewhere. It will reach here, A dash, right? So the motion can be depicted as somewhat like this because it has fallen behind, isn't it? Now, what is this deviation or bending? This is a rightward bend. First of all, how do we get to know what is rightward and what is leftward? So here, let's suppose a wind is moving. Now, if the wind, let's say, moves like this, it is a leftward bend. How? How do we get to know that this is the leftward bend? So always, if you have to find out the leftward or the rightward bend, always understand, put yourself in this place of origin of the wind, where the wind is originating. Try to look towards the direction in which the wind is moving. Your left side will be the leftward bend, your right hand side will be the rightward bend overall. So this will be leftward, this will be rightward. Similarly, here the wind is moving. Again, put yourself here. Your left hand side will be the leftward bend. Your right hand side will be the rightward bend. Okay, so that is something which is experienced overall. Now, in the same situation, if you observe this case, here we can say this is a rightward bend. Okay, now suppose an object is trying to move from A to B. So we can say that it is moving from a faster velocity to a region of slower velocity, right? Now there, what do we see? On an object which moves from a faster speed to a slower speed, the object falls ahead, isn't it? So rather than reaching B, it will reach somewhere here, B dash, again a rightward bend, right bend. What about the southern hemisphere? In the southern hemisphere, if you observe, let's assume an object moving from C to A, again the same principle, that it is moving from slower speed to a faster speed. When an object moves from a slower speed to a faster speed, the object will fall behind. So let's suppose an object is trying to move from C to A, it will end up falling behind A. Let's suppose it falls here, it comes here, right, at A double dash. So it tried to reach A, it wanted to reach A, but A was moving at a much faster speed, so it fell behind, right? So here, what is the bend? The bend is leftward. Whereas let's assume an object is trying to move from A to C. Now here, as it is trying to move from A to C, again from a faster speed to slower speed, so it will fall ahead. So here again, it will end up falling somewhere here, C dash, isn't it? So this again is a left bend. So that is why you will observe that the objects moving in northern hemisphere, they will bend to the right. Object moving between the latitudes in the southern hemisphere, they will bend to the left. But this bending is initiated because of the difference in speed, right? The difference in rotational speed that you have. So objects in the northern hemisphere will bend to the right, objects in the southern hemisphere will bend to the left in this case, always. Now, imagine if an object has to move from here point 1 to point 2, above and below equator, 5 degree north and 5 degree south of equator. Now, in between these two areas, can we not say that here the speed of rotation is going to be largely similar because the radius is going to be similar in these areas? So if the speed of movement is the same in between different places, there is no deviation. So here, that is why the objects will reach here without deviation, right? Because the speed of rotation is the same. So there is no bending immediately above and below equator. So can we say that at equator, no bending or Coriolis force is absent? Above or is absent immediately above and below equator. That is roughly around 5 degree north and south, it will be absent. What about the polar region? If I consider the polar region, now the speed of rotation at poles is 0. And if I consider even this place or even this area, any area, there will be a difference in speed. Whenever there is a difference in speed, there is a Coriolis force or a bending which is happening. So at the polar region, because the speed of rotation is 0, there will always be a significant difference of speed from other places. So that is why Coriolis force will have the maximum impact at the polar region, and the Coriolis force will have minimum impact at the region of equator. So Coriolis force, in terms of the bending that it is able to achieve, it will be maximum as you move towards the poles, minimum as you come towards equator. So that is the entire concept behind the Coriolis force. So here, if you take a look at the Coriolis force, so it deflects the winds to the right direction in the northern hemisphere and to the leftward direction in the southern hemisphere. Deflection is more when the wind velocity is high. Okay, it is maximum at the poles and is absent at the equator. Why maximum at the poles? Because the relative speed difference is going to be greater, because the poles have a zero speed or zero movement at all. So always there will be a relative difference in speed. Now the Coriolis force acts perpendicular to the pressure gradient force. What does that mean? Let's suppose you consider again the planet. Here, let's suppose you have a low pressure and you have a high pressure. So you have a pressure gradient force. What is the direction of pressure gradient force? We can say that the pressure gradient force is in this direction. Now, that is how the wind will be initiated, high pressure to low pressure. But they will experience a Coriolis force of bending. So they will experience a bend towards here. So Coriolis force is acting in which direction? It is acting in the right direction here. This is the Coriolis force. This is the pressure gradient force. So that is why the eventual resultant wind motion will be somewhat in between. Okay, so always this will act in a perpendicular manner to the pressure gradient force. Okay. Y pole has maximum Coriolis force where the speed is low at the pole. Okay, understand this, that why Coriolis force acts. Coriolis force acts due to, now in the region of equator it is not acting. Why? Because there is no difference in velocity in between the different region. Acts as there is a difference in speed of rotation in different places. Now please understand, again I will clarify and listen to this sentence carefully. An object, while it is moving between different places, only then it will experience a Coriolis force. Let's suppose an air is static in a place does not mean it will experience Coriolis force. Only when it is moving in between places of different velocity, only then it will experience Coriolis. When we say that Coriolis force is maximum at the poles, does not mean that you go there in the poles and you start spinning automatically because of Coriolis force. No. If something is moving towards the polar region, they will experience Coriolis force. If something is moving away from polar region, they will experience Coriolis force due to the motion. So there is a difference in speed of rotation at different places. So that difference in speed, if you consider the poles, speed of rotation is 0. So any other place that you consider from where the object is to move, you will get a difference in speed, very high difference in speed, because one of the factors is absolutely 0. Let's assume here the speed of rotation is 1600 km per hour. Here it is 1000 km per hour. So the difference is 600 km per hour. That is what is exerting that bend. But here if it is 1000 and here is 0, so the difference in speed is how much? 1000 km per hour. So the bending will be significant. So because the difference in speed is calculated and that is instrumental, at the poles the speed is 0. So difference in speed from any area is going to be high, to be very high. And when the difference in speed from any area is going to be very high, that means Coriolis force is going to be significantly very large and very high. Is that understood now? Or do we have any doubts which prevail? Is that understood? Prashant, you had asked this question. Okay, good. Now, we move on to the other force which also influences the wind movement, and that is the frictional force. So when we talk about the frictional force is basically the force of resistance, right? That is what is friction, force of resistance which is offered, right? So here, the frictional force is basically force of resistance, which is offered by the ground and the ground obstacles and different obstacles. Now, here, let's suppose in a particular region, you have the presence of trees, significant amount of trees, let's suppose. Okay. Now, if the wind is moving and you have, let's say, a couple of hillocks, a hill as well. Now, if I consider the movement of wind at this height, A, and I consider the movement of wind at this height, that is B, obviously, the movement at B is going to be much faster because A is going to experience significant amount of resistance, isn't it? So A is going to experience resistance, B is not going to experience any resistance at all. So that is where, because A is going to experience resistance, the speed will be slow. So that is the frictional force. Speed reduces, isn't it? So that is a major factor here. Comparatively, if you consider, let's say, a water body, seas and oceans. Water body, please again don't consider by water body a lake which is in the backyard and the pond which is there in my village where everybody comes to wash clothes. Not those water bodies. Whenever we are referring to water bodies, from now on, always get that understanding. Water bodies will always refer to larger seas and oceans. So please don't get confused that, but the river near my house, that is very wide. It is, some people say it is as big as an ocean. So can we not consider them? No. Water bodies always means oceans and seas when we are talking about this, when we are holding the discussion. So here, if you consider the movement of winds over the water bodies, so in this case, the movement will not at all be impacted by the frictional force because there is not much resistance. So that is why over the sea surface, the friction is minimal, so the wind speed will be higher. It is greatest at the surface and the influence generally extends up to the elevation of 1 to 3 kilometers. That is why at higher altitude, the wind velocity is going to be very high always. At a greater altitude, the wind velocity is going to be significantly high, right? And over the sea surface, the wind velocity is also going to be very high. So from this, can we make a conclusion? Wind speed is very high in the southern hemisphere as compared to the northern hemisphere. Can we say this, or do we have any doubt here? We can say this. It's right, B is greater than C is greater than A. So see, Tuhin, in this case, you cannot have an absolute comparison over B and C. Generally, you will find that high altitude winds, they will be the fastest, even as compared to the water bodies generally. You will find that the wind is very fast over an elevation. Here also, if you consider the elevation at a greater height, the wind speed will be very, very high. Okay, so generally we can't make a comparison. If you compare at the same elevation, then always the wind speed is going to be very fast over the water body as compared to the land area. Okay, I hope this is understood. Vivek, we were talking about so welcome to the session. So we were talking about the frictional force, Coriolis force, and the other factors of the wind movement. Frictional force is the force of resistance, which decreases the wind speed over a period of time. So when you have a resistance force, obviously the wind speed will be reduced. Okay. Now, after this, we come to the concept of onshore and offshore winds. What do we mean by onshore and offshore winds? Onshore, something which is moving towards the shore. And offshore, shoreline is what? The coastline in general. So when we say onshore winds, these are the winds which travel, which move from sea to the land. Now, when a wind is moving from sea to the land, is it going to bring moisture along with it or not? What do you think? When an object is moving from sea to land, it will bring moisture, correct? So this always ends up bringing rainfall. Very good. Brings rainfall in the process. Okay? Always ends up bringing rainfall in the process. When we talk about offshore winds, winds which are basically, they indicate winds moving from land to the sea. Now here, if you consider onshore, so imagine if the wind is moving like this. Obviously, it will bring significant amount of moisture here. It will cause sufficient amount of rainfall in the process. But when we consider offshore, offshore means what? From land to the sea. So, will it bring moisture along with it? Offshore winds, do you think it will have moisture or do you think it will be devoid of moisture? What do you think? It will not have moisture? Very good. So, here they are devoid of moisture and are dry. Okay? So that is why offshore winds are not associated with rainfall. Okay? Kajal, why did we say that wind speed is high in southern hemisphere as compared to northern hemisphere? The reason is very simple. Observe the southern hemisphere. This is the region of equator. Observe the southern hemisphere. The southern hemisphere is dominated by water bodies. Northern hemisphere is dominated by land areas. We know that speed is significant over the sea surface because over the sea surface friction is minimal. So if the winds are blowing here, the winds will have significant amount of velocity associated, isn't it? So that is why in general the speed of wind in the southern hemisphere is going to be faster. Is that understood? Vivek, La Nina have onshore winds. My dear friend, see, please first of all understand what is La Nina. La Nina does not have direct winds associated when it comes to, if you are applying the logic here, a simple unitary method that India receives more rainfall during La Nina, so it must be onshore winds. That is an absolute incorrect logic to apply. La Nina brings more rainfall in India because of very complex phenomena, because of Mascarene high pressure belt, because of the influencing of the Tibetan high pressure. So all of them are involved. So first of all, understand the basic concepts, my dear friend, and in the most politest of the form that I can tell it to you, that be attentive and careful in the basics. These concepts will come naturally to you, right? Till now, we have come to this portion. All of them who have been regular and attentive from the first hour yesterday, I'm sure they have understood that process. Just be regular, my dear friend. I will explain to you what is La Nina, why it brings more rainfall to India during the monsoon season, whether it is El Nino, whether it is La Nina. Let me make myself very clear here. During the monsoon, if it is El Nino or La Nina, both of them will have onshore winds. So El Nino, La Nina is something which happens in the Pacific. So you cannot have onshore and offshore winds from Pacific all the way to India. So it is a different phenomena. Wait for some time, it will come to you. Okay. Now we come to the factor of air circulation. What do we understand by air circulation? And why is it that air circulation is observed in different places of the planet, in between the different areas of the planet? So, we have seen yesterday quite sufficiently and in a quite greater amount of depth that when we talk about air circulation or when we talk about the solar insolation, different places of the planet, they experience differential rate of heating and differential rate of cooling, because insolation is different, temperature will be different. Some regions, they become significant, or they are the areas where significant amount of heat is observed. Some areas, they are particularly colder. So in a way, we also can classify this as some areas, they are heat surplus, heat surplus, and some areas, they are perpetually heat deficit. They are perpetually colder, they continue to lose heat. Now, eventually, you need the balance of the energy, right? Distribution of heat. So that is why, in order to distribute heat, in order to have a uniform distribution of heat, the air tends to move, the air tends to circulate in order to distribute heat. Air tends to circulate in order to distribute heat across the planet. Now here, mankind, basically, if you take a look at it and the evolution of the theories of air circulation, you have to understand that air movement has been very, very important. And understanding the movement of air has been of greater importance because in earlier days, large areas would be covered by ships. You did not have airplanes. Obviously, road transport was not developed. So ships were the chosen mode of transport. Now the sailors, the mariners, now they had to explore newer areas. Now even the ships, they were not diesel engine powered or nuclear powered. The ships would be moving with the help of the wind. So always the sailors would be interested in knowing what is the wind direction, and wind direction will be in that region for how long a duration, so that they can facilitate their movement. For the first time, it was in the 1600s. At that point of time, there was a kind of an attempt which was made in order to chart out the movement of the wind, so that you can have some amount of predictability that, let's say, if you're moving from South America to Africa, Africa to North America, what kind of wind movement you should expect. Now there, at that point of time and slightly later on, the first air circulation model was provided by Hadley. Now Hadley provided the first circulation model, and that was referred to as unicellular model of circulation. Cellular model of circulation. What was this? This was completely dependent on thermal pressure zone. It was the entire theory or the entire model was dependent on the thermal pressure zone. That pressure, low pressure or high pressure, till that point of time it was understood that low pressure and high pressure are created only as a consequence or only as a result of temperature. So for example, here what this model talked about is that, look, at the region of equator, temperature is high, so you have low pressure, right? And because the temperature is high, at the poles, the temperature is significantly low, so it is going to be high pressure, right? So here, what was thought to be is, let's suppose this is 0 degree, this is going to be 90 degree. So 0 degree has got low pressure, 90 degree or the polar region is going to indicate high pressure. Now here, because of heating, air is going to rise up. That is what is going to create the low pressure. Air is going to hit the troposphere or the tropopause. It will diverge. It will move. Here the air is already sinking. So in this region, there is a vacancy created in top. So the air will move. It will sink. And on the surface, it will move again. And this is a formation of a cell. So Hadley said that, look, there will be a high pressure created at the region of the poles. There will be a low pressure created at the region of equator because of heating. So at the region of equator, the air will rise up. It will move towards the poles. And on the surface, the winds will be moving from polar region to the equatorial region. Now, as per this concept, here, the air, let me indicate air by a different coloration pattern. The air would rise up. They would be moving towards the region of the poles. At the region of the poles, they would be sinking. And on the surface, they would be moving. The same in the case of southern hemisphere as well. Now, in this case, Hadley indicated that in each of the hemispheres, you have the formation of a cell. One cell of circulation in each hemisphere. And that is why this was referred to as unicellular, because you have the formation of one cell in each of the hemispheres, hence unicellular. Now, this was accepted at that point of time because it made sense overall that, okay, he's saying that it is hot, hence low pressure, and equator, yes, it is low pressure, poles, yes, it is high pressure, so it might happen. In the 1800s, you had a study carried out by an American climatologist with the name Ferrel. Now, Ferrel, basically, when he studied the wind movement, he made few observations, and the observations were very simple, but the observations completely nullified what Hadley had said. The first observation that he made was that, look, there can never be any wind, regardless of how strong that wind is. There can never be any particular wind which is going to be so strong that continuously from the region of poles, it is going to drive towards equator without any interference, or because As the wind travels on the surface, its velocity keeps on reducing, and after a distance, the wind is not active anymore. And by this point of time in the 1800s, Coriolis force as a fundamental was also understood, that it is going to have a rotational motion. The wind is going to have a deviation. So Ferrel also pointed this out, that look, if you are saying that the wind is moving from the region of equator, it cannot be possible that the wind will reach all the way around the poles. Because if we talk about the upper air wind movement, the wind will experience a rightward bend, and it will never be able to reach beyond a particular point, and it will never be able to reach the region of the poles because of the bend. So the unicellular model was discarded. Observation was also made that if the unicellular model is true, that means on the surface, everywhere you will observe a wind movement towards the equator itself. But that is not the case. So after this came the inception. So this was the unicellular model. Unicellular model, which was provided by Hadley. And this basically was dependent or based on the concept that pressure zones are created only due to temperature. This was concept is flawed and incorrect. Why? We have seen that pressure zone is dependent on other factors also. You have the dynamic movement of wind, which can also create low pressure and high pressure. So based on these factors, based on the Coriolis force, now here if I ask you a simple question, even though I have given the answer of it already, when the wind is circulating in the upper atmosphere, will it experience a Coriolis force? Yes or no? What do you think? When the wind is circulating in the upper atmosphere, that is in the region of troposphere, at the tropopause, will it experience Coriolis force or not? Good. It will experience Coriolis force, because there again, it is even in the upper atmosphere, it is moving from an area of slow rotation to an area of faster rotation and vice versa. In fact, when the wind is moving in upper air, here the speed is going to be higher. So higher the speed, greater is the deviation. We have seen earlier that the deflection is more when the wind velocity is high. And wind velocity is high where? At an elevation, the wind velocity is high. That is why the upper air movement of wind will also experience deviation, and that will be a significantly substantial deviation which will happen. Now, this all thing was understood in the 1800s when Coriolis force was understood overall as a phenomena. And then later on, you had the postulation of what was referred to as the tricellular model of circulation. Tricellular model of circulation. Now here, guys, pay attention to this. From the very basic we will initiate, and we will be using the concepts of thermal and dynamic pressure zones here, convergence and divergence of air that we have talked about. Just forget all the preconceived notion that you have in your mind. Think about it. Assume that you know nothing about it. You just know what is dynamic pressure. You just know what is thermal pressure. You know about the rise and the fall of air. That is it. From that, let us approach this. Trust me, you will understand it to that extent. You will never need to revise it because you will be able to draw it on your own. So that is the ideal aim. Let us see how far we are successful in that. So let us consider the ground surface. Now, we will consider one hemisphere. In the other hemisphere also, it is the similar thing. So here we consider different places: 0 degree, equator, 25 to 35 degrees. It is generally 30 degrees, but let's assume, right? 25 degrees to 35 degrees, north, roughly 55 degrees to 65 degrees, and then you have 90 degrees. This all is understood in 1800 and we are still understanding it. Yes, 1800s, that is where you have to appreciate that without any of these visual medium, people were able to imagine all this. In the 1800s, when they understood this concept of Coriolis force and everything, understand that none of them had the experience of exploring the entirety of the world. Based on the various studies and the biographies and the experiences left behind by the older sailors and the older mariners and the climatologists, they were able to imagine things. So imagination has got a great power. It is a different matter altogether that we use that power for all the wrong reasons and we imagine different things, that once I become IAS officer, my friend will get to know what power I have. So if we use the imagination to a correct aspect, this subject is something which will become a cakewalk for us. But let us see. Here, when we talk, the amount of air circulation will be equal in all area, Harishwar. It is in practical scenario, it is not, but we will come to it. I will show you the real time scenario of what happens on a daily basis. That is also something I will show. Don't worry. So here, around the region of equator, there will be significant amount of heating, right? Generally, roughly around equator, there will be heating. So as there is heating, the air in this region will rise up. Now that air will rise up as long as it is warmer than the surrounding. Let's assume it rises up to the region of tropopause. And here let me also draw a small planetary image, and this is for upper air circulation. This I will use for upper air movement only, not the ground surface. Okay. Now it rises up till the region of tropopause. Upon reaching the tropopause, it will diverge. One will go towards the southern hemisphere, other will go towards the northern hemisphere. Right? Now look at the upper air movement. It is this particular portion is here. So the one moving in the northern hemisphere will bend to the right. Bend to the right. Now here you will observe that due to the bending, and also as this air moves in the region of tropopause, it will get colder. Remember we talked about it, the more time that the air spends in that vicinity where everything is cold, it will get much more colder. And here you will observe that the air tends to accumulate in a region due to the rightward bending. So the air will accumulate, it will become very cold as well. So then what will happen? The air will experience a sink, isn't it? If I take you back to, I think, yes, here, as the air spends more time in the upper region, it will get colder, and eventually what will happen? It will sink regardless of what is the temperature at the ground surface. The air will sink, isn't it? So here similarly, if you observe in that scenario, eventually the air will sink. Now this air sinks at the region roughly around 30 degrees, generally around 30 degrees, but it changes sometimes. So there, when it is hitting the ground surface, this will diverge. One portion will go here, other portion will go here. The portion which goes in this side towards the equator will rush towards the equator. Why? To fill the vacancy which has been created due to rising here. Here also air will come, rush in. When it comes towards equator, it will also get heated up because equatorial region is warm. So it will also rise up, isn't it? Now, this air goes towards the polar region. Meanwhile, in the region of the poles, it is very cold, right? Very, very cold. As I told you, even if I wake you up in the middle of the night and I ask you what will be the temperature at the poles, you will all say that it is very cold. So because it is very cold means here you will have sinking air, high pressure. It will move. And this air is moving. Eventually, it will converge here. Now, when there is going to be a convergence, where is it that the air will go? Will the combined air move towards 30 degrees? Will the combined air move towards 90 degrees? What will be the movement of air in this case? Around 55, 60 degrees. What do you think will be the movement of air? Correct? Good. It rises up. It will converge. It will rise up. As it rises up, eventually it will hit the tropopause and it will diverge. It will diverge. One portion goes significantly towards 30 degrees. There it encounters this particular upper air wind which is already accumulating there, and there it will start to sink. And in this region, because the air is sinking, so there is a vacancy created in the upper area. So this air will go to fulfill that. So there is a circulation which is achieved, isn't it? So that is how the circulation is observed. I will repeat the entire process again. Listen to this carefully. Around the region of equator, first of all, think about it chronologically. Around the region of equator, there is going to be sufficient amount of heating around the region of equator. Okay. Now, because there is going to be sufficient amount of heating, the air also will warm up above it and the air will start to rise up. As the air starts to rise up, there will be vacancy created near the ground. So nearby air will come to fulfill or fill that vacancy. They will rush in. Now this air, as it rises up, eventually it will reach the region of tropopause, right? And at tropopause, it cannot rise any further. So it will diverge. One part goes in the northern hemisphere, one part goes towards the southern hemisphere. Now, imagine the upper air circulation. This point, let's say that I hope you are able to see on the screen the upper air divergence. Imagine this point is indicated here. So as the wind is moving in the upper air towards northern hemisphere, you will observe what? You will observe a kind of a circulation like this. There's a rightward bend initiated, isn't it? Now here you observe that the wind is unable to go towards the poles because of the rightward bend, and also the wind cools down quite sufficiently in the process because at the top of the troposphere, the temperature is -60, -70 degrees Celsius. So the wind cools down very sufficiently and it is accumulating here. So when the wind is very, very cold and accumulates, what will happen? It will sink down because colder air is heavier. So it will sink down, the wind will sink in this region. Here it will sink and it will reach where? The ground surface. So on the ground surface, you will have or you will observe the creation of high pressure, because of sinking air. Now the air, when it hits the ground surface, thereby it diverges. One part, obviously, because after the air hits the ground surface, it cannot go anywhere else. It has to diverge, right? Again, I will take you back to the original portion where we saw this. Observe, as the wind hits the ground surface, it has to diverge eventually, isn't it? It diverges. So here again, if I take you to this particular scenario, as it hits the ground surface, it diverges. One part goes towards the equator, other part goes towards the poles. The portion which goes towards the equator, that experiences, or that again is going to fulfill the vacancy created at the region of equator due to rising air. This air, as it reaches the region of equator, again it gets warmed up, so it rises again. Now, one portion has started moving towards the polar area. Now, meanwhile, at the region of the poles, because of extreme high temperature, you have the creation of another high pressure, a thermal high pressure, Thermal high pressure means the air is sinking, right? Thermal high pressure means very cold condition, so the air will also get cold. So air is cold means it will sink, it will fall down because colder air is heavier. It sinks, it hits the ground, creating a high thermal high pressure. After that, it will move, right? It will move, and as it moves, it encounters the wind coming from the tropical area. So in the subpolar region, again, you will have a convergence of wind, and the wind here has got nowhere to flow. So the wind will rise up. So this will again create a low pressure. And that is how here the winds will rise up eventually and they will fulfill the entire circulation. Is this portion understood? The basics of it. Is it understood? We will come to Azure side, don't worry. Is this understood till now? Okay, good. So here you observe why it is referred to as a tricellular, because you will observe that 3 cells are formed in each of the hemispheres. This is what is referred to as Hadley cell. This is what is referred to as the polar cell. And this is what is referred to as the Ferrel cell. Now here, the low pressure created here, this is also going to be a thermal low pressure. Thermal low pressure. Whereas this low pressure that you see, this is this low pressure a thermal low pressure or dynamic low pressure? What do you think? Because the temperature on the ground surface is cold. So why is there a low pressure created? Beautiful, very good. It is a dynamic low pressure which is created. So here, basically, you will observe there is a dynamic low pressure created. So this is what is subpolar low pressure belt. Dynamic low pressure, that is subpolar low pressure belt. Here again, at 25-30 degrees, temperature is high, but still you have a high pressure here. Why is this high pressure? Thermal or dynamic? Here again, You have dynamic pressure because of sinking of air. So this is dynamic high pressure. And this is subtropical high pressure belt. Okay? The more about it and details about it, about the pressure zones, about the wind movement that is observed, that is something we will do after the break. So why is there a convergence and divergence at 30 and 60? So see, I have not taken 30 and 60, Benita. That is why I have taken 25 to 35 and 55 to 65. It can happen at 55 also, it can happen at 60 also, it can happen at 62 also, right? If I would have taken 30 and 60 degrees only, your question is justified. That why only at 30 degree, not at 29, why not at 40? But that is not the case. Sometimes this high pressure can happen at 25 degrees, sometimes 35 degrees, sometimes 30 degrees. Sometimes this low pressure can get created at 55, 65. Now, why only in that range? Because that is where the convergence and this is where the accumulation generally is observed. Because from the equatorial region, as the winds rise up, they will always experience a divergence, and that is where, or a deviation, and that is where eventually they will accumulate in a particular zone or distance away from equator, and that is roughly around the region of 30 to 35 degrees. Okay? Have patience, my dear friend. Azores High, I will talk about. See, this is the region of Azores High. Okay? This is your Azores High. We will come to it, my dear friend. Please don't get that FOMO feeling that that is not to be taught. I will come about it again. I will come to it again. And because I understand many of you will have some doubts or the other. So we will talk about Azores High, the Aleutian Low, everything we'll talk about after the break. Okay? I hope that you can have patience up till the break. So let's take a break. We'll have a lunch break, 1 hour, 2:10. We will be back and then we will continue. Roshan, excused. What is your one question? Separate notes of entire subject or together? Topic based, Roshan. Topic based notes if you prepare for all the subjects, for different subjects. Eventually, I hope you are preparing in an A4 sheet of paper so that it is easy to sanitize the notes later on. So that would do. In warm westerlies, cover nearly 60 to 65 degrees. Yes, roughly. We'll come to the westerlies also after the break. So we take a break. After that, we come to the permanent winds, the local winds, the pressure belts, and we move on. So take a lunch break and we'll be back by 2:10. Okay?